All right, so I think today we can probably finish up our discussion of one-dimensional proton NMR. And so then the next thing we're going to do is talk about a C13 NMR. So up to now we've talked about kind of the three main pieces of information that we can gain from proton NMR. We talked about integration, we talked about chemical shift, and we've talked about splitting. So today what we're going to do is we're just going to spend a little time practicing, working some problems, and then we're going to talk about two other types of one-dimensional NMR experiments. So this decoupling experiments are a way that we can determine directly whether two protons are coupling with each other instead of just matching coupling constants. And we will talk just a little bit about nuclear Overhauser effect spectroscopy, and this is a way we can do it as a one-dimensional experiment to determine which protons are within close spatial proximity. And we probably won't make it to the carbon NMR today, but I put it down there anyway. All right. So are there any questions before we move forward? Is everything seeming reasonably clear and useful, hopefully? Well, we haven't practiced anything yet, so. All right, so let's just think a little bit first about pieces of information that might help if we're trying to determine a structure. And one thing that can help is just determining the number of unsaturations in a structure if we're given the molecular formula, right? So I think the there's a couple of ways you can go about this. First is to perhaps determine what are the maximum number of hydrogens that could be in a structure for a given number of carbons, right? So we probably all know if we have CN, we have N carbons, how many hydrogens could we have? 2N plus 2, right? And this would be something that we would refer to as being totally saturated, right? It has the maximum number of hydrogens. It's just saturated with hydrogen. We can have unsaturations, though, and so unsaturations usually involve the loss of pairs of hydrogens, of two hydrogens. And what structural ways can unsaturations be accounted for by?
Double bond.
Yeah, or in a more general sense, pi bonds, right? Right, they could be double bonds or triple bonds. What else?
Substitution of oxygen, or wait.
Well, not so much substitution.
Maybe it's a different function of substitution.
What?
Like a dye substitution.
No, just the number of substitution isn't going to affect the saturation.
Oh, so like the
What?
carbonyl
Rings. Right? If we make a ring, we need to remove two hydrogens in order to join the ring together. And so unsaturations gives us some idea of whether there are pi bonds and or rings. Okay? I usually use this formula. I think I learned it in the mass spec book in this same kind of class, and the way it was done is we calculate the number of unsaturations equals the number of carbons in the molecule minus the number of hydrogens divided by 2 plus the number of nitrogens divided by 2 plus 1. Okay, other atoms that we could fit in here For example, if we had silicon, it would be counted by carbon, right? It's directly before carbon. It has the same number of bonding. With the hydrogens, we also include the halogens or deuterium, atoms that just make one bond. And under nitrogen, we could put phosphorus. All right. So as we go through some of these examples, one of the first things to do oftentimes to make it easier is to calculate the number of unsaturations. It'll give us some idea about the structure right away from the molecular formula.
So halogens can go under hydrogen?
Right. Because if you have a structure, think about it, if you're going to put a halogen on it, you essentially take off a hydrogen, put a halogen. Right? So it doesn't affect the unsaturation number. And notice that oxygen doesn't even show up in here. So likewise, oxygen, we usually just, if you have an OH, we just substitute it between a carbon and a hydrogen, or an ether just between two carbons. And the only way that we have an unsaturation is if we have a double bond, a carbon-oxygen double bond or something. All right? So let's just look at some, start out simple here. So just take a moment here, calculate your unsaturations, and see if you can come up with some structure for this proton NMR. So how many unsaturations do we have? Just one. Right? So what do you think about when you look at that proton NMR? What would you probably do first?
Methyls. Methyl.
Right? We probably have a methyl over here.
And that would be
And how do we determine that that's a methyl?
integration.
Right? The chemical shift and probably the integration, right? So let's take a look at the integration. What do you think the ratio of the integrations are?
2 to 3.
2 to 2 to 3. Right? So if that's a 3, then what are the other two groups? What do they represent? Just CH2 groups, right?
Yeah.
So it looks like we probably have just CH3, CH2, CH2. Right? So how does that compare to our molecular formula?
Some symmetry.
Right, there's got to be some symmetry, right? So what about the number of hydrogens?
Yeah, together and double it.
Right, so we have to exactly double it, right? So it probably means that we have a CH2 over here, CH2, CH3, right? And so those have to be exactly symmetrical. So what do we have left over? Just a carbonyl group, right? Right, so do the chemical shifts fit?
Yep.
Yeah, so these protons being at 2.4 look good for next to a carbonyl. The CH2's in the middle, right? They're essentially, we can see they're essentially coupling equally to the CH2 and the CH3.
Yep.
So we have 5 protons plus 1. We have 6 peaks, and then the methyl groups on the end. All right? Simple. All right, take a look at this one. So how many unsaturations on this one?
0.
None, right? All right, so it's already giving us that there's an OH. So our task is to figure out what, if we have a 7 carbon piece, where is that alcohol going to be, and whether we have any kind of branching in the structure.
We can tell from the left, at the very least, in the equation that 3.5 is just one proton.
Right, so this looks like 1, right? So what does that tell us about the structure?
Branched. It's branched and bonds to the OH.
Well, or that the OH at least has to be what type of alcohol, what level of substitution?
Secondary.
Has to be a secondary alcohol, right? Because we know that there's only a single proton. Then, this integrates for 1, right? Which also integrates for 1 on the alcohol. So it's a little trickier looking at these other ones because they're so big. So how about down by the methyl group range? How big do you think that is? Yeah, probably 6. Right, so how many does that leave us left over? 8 under here. Right, so it's just a big jumble in there, right? So let's just think about the possibilities then. Do you think that the carbon chain could be branched?
Something weird's happening, so it's disgusting. The 1.5 to like 1.1 is
Mm-hmm.
kind of gross.
Yeah, well,
So that probably means there's some branching going on.
I think it's a long chain. I imagine. And other splittings.
right, all the splittings, what else, if we had a branch structure, what else would we need to see in here?
This is singlet or doublet. If we had 6 protons in there, we would need to see a doublet.
Well, if we have a branch,
We have to say CH group again.
we have to see more methyl groups,
Maybe more.
right? We only have 2 methyl groups, so there can only be 2 ends. If we branch it somewhere, then that gives us 3 ends, right? So I think it can only be a straight chain. And so let's think about the chain. So if we have 5, 6, 7, we already decided it can't be on the end, right? It can't be a primary alcohol because the hydrogen next to the alcohol is only worth 1, right? So we could have it here. We could have it here, or we could have it here. So
It
can
kind of looks like a head, but I'm not entirely sure. That 3.5.
the 3.5? Yeah,
It's kind of hard to say.
it is kind of hard to say.
I'm not sure I trust that completely.
Yeah. Are there any of these that we could rule out?
Symmetrical.
Right, so we can rule this one out, right? Because that's symmetrical and it would give us a much cleaner spectrum, right?
We had the methyl right next to the OH group. It should be pulled way farther up than it is.
Well, it also would show a doublet instead of a.
Yeah.
Yeah.
I think you're right on that.
Well, we got to look at these, the methyls here, though. Are they just right on top of each other, or is there some kind of offset or something?
A little offset.
A little offset.
Yeah, so do we,
I think the middle one.
because there's this little peak right here, too.
I think it's the middle one.
So if we had the middle one, then essentially we should have, this is a triplet, this is a triplet, right? We should have somehow 2 overlapping triplets. And if we had this one over here, this should be a doublet, and this one should be a triplet. right? So we kind of have to sort out whether we think what we think is happening down there in that methyl group range. I think there's two triplets overlapping, or a triplet and a doublet overlapping.
And a double.
It'd be the smallest doublet ever.
Yeah, it'd be a really tiny stuff.
I don't,
I'm kind of.
I can't convince myself that that's a doublet either.
I'm kind of leaning towards triplet as I look at it.
Uh-huh.
That's,
Well, I would say that this little one that I pointed out on the side, so that's got to be part of probably a triplet, right?
right.
Oh,
So if we have a triplet like this, one, two,
and then.
and then what do we have overlapped on top of that then?
Another triplet.
Another triplet, so how would it be overlapped? Just like this, 1, 2, 3.
Yeah.
Yep.
So that would give us 1, 2, 3, 4 peaks. How many do we see? 4. 1, 2, 3, 4. But this side over here should be about the same size
Yeah,
as this
that's
size
what I
over
was
here.
wondering.
Oh.
So I think what it actually is this triplet like this with a doublet overlapping like this.
That's what I was wondering.
Because that makes this middle one a lot taller than the one on the outside. And then they're overlapped in the middle, so that's the biggest peak, because it's a doublet and the edge of a triplet
So
overlapped.
is the first one that you drew a doublet of triplets or triplet of doublets?
Does it matter?
Yeah, because when you list things in the JBot, you have a DT followed by 2 JBot.
Yeah.
So would you call that a DT or a TD?
That was just multiple.
And then would the second one be called a DT or a TD?
Yeah. Well, the first one would be a doublet of, well,
They're not even related though, are they?
doublet of triplets, or,
No?
yeah, it's not one multiplet though. There's just either 2 triplets or there's a doublet and a triplet. Right? There is no extra coupling constant in there because it's not a single signal. There's 2 signals that are just overlapping.
Yeah, it's not splitting.
Right, that's not, the separation of those two is not based upon coupling. Right? So this would just be a triplet and a triplet, or a doublet and a triplet. Right? So the doublet and the triplet fits this pattern, would fit this structure, and this pattern would fit this structure. All right, so it's a little bit hard to tell, right? So I think we at least narrowed it down to those 2. But, you know, it's not super easy to tell between those 2. Okay? I think this end one is actually the correct one from what I got the structure, the NMR from. Since I had the cheat sheet. All right, here's another one. This little peak right here on the side is the solvent.
There, 7.26.
Yeah, something like that. Yeah, because it's over here. All right, here, let me see if I can. Where are those? Okay, here's the integration there and here. And I think that this one, I can't even hardly see that. I think it was somewhere like here and here.
Okay.
All right, so how many unsaturations on this one? 4. All right, so what does that tell us probably? Yeah, there's probably a benzene ring, right? 4 more, then there's a good chance we got a benzene ring. So how many substitutions do we have on the benzene ring?
I think just one.
Probably just 1, right? Because this is probably a 2 to 3 ratio. And then this is probably 2 to 2 over here. And then 1. So these two are looking a little second order, right? They don't really look quite like the patterns we would expect. So what do you think about those two? They're equal in integration. Or they're coupling with each other, right? What? Why are you saying a ketone though?
You can, there's only 4 unsaturations.
Okay.
Right, we got 4. We can only have the benzene ring. That takes up 4 unsaturations. Right? 3 double bonds and a ring. So let's just focus on the part we can actually see. Right? And then we can figure out what to fill in with what's left over.
So you can see there's, so the far right, the 2.0,
Mm-hmm.
that proton.
Doesn't show much, does it? So what do you think about that then? Yeah, could be an OH.
Pretty low OH, yeah, but
Well, in chloroform.
Yeah.
I can convince myself of that.
Uh-huh. Right, there's not much structure at all to it, so that maybe suggests that it could be an OH.
Could be in
So it's just going to be
What about these?
Ester.
What about these 2 at around 4 though?
CH2,
Right, so it has to just be a CH2, right? And they're connected to something on each side.
It's connected to
Ester
it's
alcohol?
connected to ester, yeah. No, it's the oxygen bridges the benzene and the alcohol, or the ethanol.
Yeah.
Sorry,
Oh,
that's what I said.
like this.
Ester alcohol.
Oh, we're still missing.
Well, there's no ester, right?
Good ether, I think.
It's an
Sorry,
ether.
not ester.
OH.
Just so.
That's one lane.
Right, because notice that both of those CH2s are very close in chemical shift, right? So it's likely they're connected to a similar type of functional group.
Oh, yeah. Okay, let's see that. Okay.
And then what about if we look at the benzene region? You know, it looks like those are a little funky too. Like maybe we have some of that magnetic non-equivalence going on. But usually if we kind of ignore the real small stuff, we can kind of get signals that are, you know, near to what we would want. So to me, that these, not including the solvent, looks kind of like a triplet. And then we could have a doublet here, and then a triplet here that's overlapping with the doublet. right? And so the doublet would be these two protons that are ortho to the substituent. So does it make sense that the chemical shift is the most upfield of the benzene protons?
Can you repeat what you just said?
Does it make sense that the chemical shift for these two orthoprotons would be the most upfield for the aromatic
Yeah,
protons?
because the resonance form would put the electron pair.
Right, because the resonance goes this way, puts these most upfield, right? Because the more electron density, the more shielded they are. Okay, so which other signal should be more upfield?
Para.
The para,
Which would be-
right? Because we can push the electron density around to the para position. So this one would be this triplet because it's coupling to a proton on each side, right? And then the more downfield ones are these two here that are equivalent, and they're going to be down here. Right? And we'd kind of, for that side chain, we'd kind of expect those two to both be triplets, right? But I think it's just because their chemical shifts are close together that they become second order. Right? Does that make sense?
They became second order because their chemical shifts
Are
similar-
close, right?
similar to
As the
equivalent.
chemical shift becomes closer to the actual magnitude of the coupling constants, then it starts to get second order. You know, protons that have close chemical shifts that are highly coupled with one another will cause the second order effects. All right. Do we have another one? We do.
I have a feeling if we had the IR for this one, then
Yeah, might help,
we have a
right?
good idea.
If only. It's always greener. The pasture's always greener on the other side. Hmm?
It's a pair of substituted benzoic acid of methoxy group.
How many unsaturations? Let's take it one step at a time.
Malic acid.
5. So how many substituents do we need? 2, right? Because we essentially have 1 to 1 to 1 to 1 in the benzene ring area, right? So we have to have a di-substituted benzene.
What is this really small kicks right there? This is
Is
just
that one
like
proton times?
This one is way out. So this is the chemical shift. That's at 12.2 or something. And this times 32 means that they
big line.
blew it up 32 times as well for us to be able to see it very well. So it's far out there and it's very broad.
This is chloroform.
No, not chloroform.
Is it the solvent is chloroform?
Oh yeah, probably. Yeah, here's the solvent right there. Huh?
I haven't been able to see the OH and see the nitrile.
Mm-hmm.
I'm wondering if sorry.
Well, I think for being that far out, we kind of have two possibilities. You know, kind of the classical one to be broad out at 12 parts per million is what? Carboxylic acid, right? And it's also possible sometimes that you can get phenols out there as well. Okay, if those are all 1, what about this peak down at 3.9? It's probably a methyl group, right?
Yep.
And so what do we think that's attached to? Oxygen. Here's our OCH3. Okay, so we have a dye-substituted benzene ring. Let's look at the splitting patterns. Try to determine what the pattern is. What's the orientation?
It's not our para.
It's not para,
It's still that much.
right? So how can we tell? Right, we don't have 2 doublets, right? So we have 2 other possibilities. We could either have ortho
Yep.
or 1,3 meta. Excuse me. Okay, so oops, I wrote too many H's here. There. Okay. So we see a big triplet here, right? These are like a doublet of triplets, right?
And then on the reverse side of the second order,
Over here.
yeah, you have the doublets of doublets, it looks.
Yep. Even doublets of doublets of doublets, it looks like.
It's pretty weird.
Yep.
And then this one, what about that? Looks like maybe a doublet of doublets or something. But notice, I think the important thing here is this signal here has no large couplings. Right? All of the other peaks have a large coupling. Right? So the large coupling, what's that going to come from? Well, not second order. What's the largest J value in a benzene ring?
Adjacent.
Adjacent, ortho, right? Adjacent coupling is going to be bigger. You said that was usually 6 to 8 hertz. Meta could be more like 1 to 2, and para is more like 0.5 or something usually. So it means that we have 3 protons that are coupling with each other.
The largest J value of benzene rings meant what again?
Is the ortho coupling, right? They're just adjacent to each other. That's kind of, I think, what we would expect if we just, thought about this. So I would say this one that looks very symmetrical is kind of one that's in the middle, right? So let's just write these as, I'm going to just call these A, B, C, and D. All right? So we can look at either C. I think the key one's either C or B. So let's look at B first. It's a proton that has no large ortho couplings. So which proton would that be in either of those 2 structures?
The middle of 2 substitution group. Like in
Which one?
3, the right one.
On the right?
Yeah.
Over to the right,
Yeah.
right?
The right
So
one.
it has to be this proton here, because that has no other protons that are ortho to it.
Yeah.
Right? So it's only seeing meta couplings and or para. Okay? What about C?
Would be the parallel to the parallel position of the
Right, so that would be over here, because that's this one that sees two large couplings, right? And we can see that they must be the same. The J values are the same going to each side.
That's why it looks so nice.
Yep.
I was gonna say, here's the second.
And then the other ones then have to be the other two. Right, so let's just choose one, A and D. So if we have a methoxy group, what else do we have left over in our structure?
So it goes
A carbon
to the overflow position of the
and unsaturation.
Right, so we have an OH. Right, we have to have an unsaturation too. So we have to have a carbonyl as well. So I think there's two possibilities here based upon these two possibilities. Right, one would be that we have a carboxylic acid and a methoxy group. The other one would be that we'd have a methyl ester and a phenol. Right?
I think looking at that,
phenol, you need to
Looking
consider
at the-
about the number of carbon.
Hmm?
We also need to fix the formula, right?
Check the formulas,
no.
as in, I mean.
So okay.
So we still got 2 carbons left.
Yeah, 2 carbons left.
Two carbons left. We have the methyl group and we have a carbonyl.
Yeah,
Right.
that fits.
Okay, so if we look at how I've labeled the benzene ring here, and proton D here is the most upfield. So do we put an oxygen next to that, or do we put the carbonyl next to it? An oxygen. Here. The carbonyl is going to go over here.
What was the other one that you could have guessed, the ester?
Right, so I haven't finished that yet. So we have two possibilities now that I would say. We could either have
Ester.
the ester here and the OH,
There it is, thank you.
or we have a carboxylic acid and an OCH3. Right? So, you know, so I got this out of our book, and our book in the answer key, which you guys don't have, says that it is this. So what do you think about that?
Sure.
Yeah, you got 2 other stuff.
Yeah, so I don't think that that's right.
Yep.
Right? Because if it was right, then we would see all of the aromatic peaks coupling with each other. We'd see essentially 2 doublets or maybe doublets of doublets for the outside ones, and the 2 interior ones here and here would look more like triplets, because both of them have 2 ortho couplings. Right? So I think that this structure that they had in their answer key is not right. But it's a little hard to tell between these 2 possibilities down here. For me, looking at this OH here, it feels more like it's the carboxylic acid, like this. But what I did, not that this really solves the issue, is that I went into this prediction website that I show you guys the couplings last time. Did I tell you what the? It's like, what was it called? NMR DB or something like that. I'll give you the. I think I had it written on there last time, right?
Tatiana in our group, she uses that website.
Oh, okay. So here, what I did. This is the proton predicting part of it, right? So you can I think the part where you actually draw the structure is off to the side. I chopped that off. But I drew in that structure, predicted the spectrum. So this is the what the book was saying, right? So it doesn't show the OH, right? Because it just can't predict it very well. So it doesn't show that. And I know these are really small, but notice that this is essentially a doublet, a triplet, and a doublet. Okay? Which is not, well, they're actually saying they're each a doublet of doublets. So here's all the chemical shifts and everything up here as well. But all of them have an 8 Hertz coupling to them. That's the ortho coupling. Okay? Which we saw one signal that did not have the 8 Hertz coupling. So let's try one of the other meta coupling that we are saying. So here is meta with the methyl ester and the phenol. And notice that, here's this triplet that looks a lot like that big triplet that we saw. And this signal right here has no large coupling. Right? Even though it does say they're all still doublets of doublets of doublets, but this one has no 8 Hertz coupling. All right, so this fits much better. And actually, the chemical shift is pretty close between these. What if we switched it to the carboxylic acid and the methyl ester? Do you think it's going to change very much?
There might be a shift maybe in the triplet, I'm sorry, the singlet on
The singlet, from what I've seen with
Up here?
the, yeah,
the stuff I've
I don't know
done,
how much.
Mm-hmm.
it should be,
All right, so let's see. This one's at 3.8.
and so the methoxy should go.
In software. This one is now at 3.75. So,
No difference.
not much difference, right? And the actual spectrum looks a lot the same as well. It still has, like we would expect, this signal here with no large coupling. It has the big triplet, and then the other ones. Right, so it's, at least from this prediction, it's a little hard to tell between these two. But I think this is another case where perhaps if we had an IR spectrum, right, we should be able to tell the difference between the alcohol and the carboxylic acid.
Yeah.
All right, but it's a nice tool to be able to draw these in and kind of predict these. All right, let's do another one. This is so fun.
Just fine.
All right, so how many unsaturations?
Two.
2 unsaturations. We got 1 oxygen. Do we have any double bonds?
Have to.
Huh?
Have to.
Well, are there any protons on double bonds?
I don't see any.
No, because those would be way down off this. Off,
Ring.
Ring and a carbon.
Oh,
maybe.
Or 2 rings. 2 rings. I was thinking 2 rings too.
Maybe.
So let's look at our integrations. So this is probably 1, right? So this is 2, 2, 1,
maybe 4.
maybe 4. So what about this 2? So presumably this is a CH2 group at 3.6.
Connect to an oxygen.
Yeah, probably next to an oxygen, directly attached to an oxygen. All right, that's too far downfield to be next to a carbonyl.
.4 is probably OH.
Yeah, I think you're right. Which it has actually a surprising amount of structure to it. But I think if you have more dilute solutions, then you can start to get some coupling. There's less hydrogen, intermolecular hydrogen bonding.
Is the one all the way on the left at 3.6 connected to the one at 1.9, the triplet?
The one at 1.9. I don't know. Do those coupling constants look like they match?
It's switched.
Right. But what about the size of the coupling constant?
What do you mean by coupling constant again? Are you getting coupling and J values and all those words?
Those are the same,
Okay.
right? It's how, when we have coupling, how far apart the peaks split, right? And when 2 protons couple with each other, their splitting will match.
Those splittings do not match.
Those do not match, right? In fact, the one at 1.9, so this splitting, is there anything that does look like it matches?
Part of the CH, the doublet or triplets.
Yeah.
Yeah, this one looks like it might couple. And who knows down in that big multiplet area, right?
But does the doublet or triplets, does that match with the one at 3.6? The triplet in there?
I don't know. It looks like it could.
Because that's what I was thinking, was that the triplet matched the triplet at 3.6.
Oh, uh-huh.
I didn't look at the matching between the one at 1.9.
Okay. It possibly could. But then again, we just don't know what's in here, right? And this is probably, what do you think about this? 4 protons.
CH2.
Yeah, this is probably CH2, CH2, and they're also coupling with each other, so it's very second order in there. And then they have to couple out to other things on each side.
It's a propylene 3-member ring.
Cyclopropylene.
Yeah.
Well, that would only be 1 unsaturation. You mean so something like this?
That'd be crazy unhappy.
Yeah, that would be
I don't know if
crazy.
I like that, yeah.
No, yeah, exactly.
Probably not.
Wait, 1, 2, 3.
So how else can we add up to 2 unsaturations?
Triple
Yeah, either double bonds or triple bond. Here we have one proton with a very small coupling going to a CH2 with a very small coupling.
This is alpine.
Yeah.
Yeah.
So this coupling is this called a propergillic coupling. And so this is usually 2 to 3 hertz. So then this would be the proton at 1.9. These would be the protons at 2.2. Right, and then we essentially have CH2, CH2. These are the ones that are down here. And then what do we have left? CH2OH. Yeah, those triple bonds you don't think of that much.
Would have been nice to have the IR.
All right. So you got to keep your mind open to the possibilities, right? Okay, so let's. Oh, this is just. I had this table, I think, maybe earlier in yours. So this is actually in the appendix in our book. I remember there was actually a Journal of Organic Chemistry paper that had all of this at 1.2, and this is a really useful table. So I guess we're just talking in general just about different solvents, right? So things that you might think about when you're choosing an NMR solvent is your compound has to be soluble in it, for one thing, right? Usually we use deuterated solvents, and so especially in the Proton NMR, if the solvent is protonated, then the proton signal for the solvent is very huge, right? And so if it's deuterated, we make that peak much smaller. You'd like to have it available, not cost too much, unless you have just a specific need. You can get solvents in differing levels of deuteration too. You can get, some solvents are more like 99.9, but you can also get, kind of what they call 100% deuterium as well, which isn't quite 100%, but really it depends upon the concentration at which you usually run your samples. So, for most synthetic applications, you always have enough sample that you don't need the super high, deuteration rate. But if you have, for some reason, tiny samples, right, and you want the residual proton signal to be small, you need to have a very high deuterium rate. So like when we were doing natural products chemistry, if you only have a milligram or less of sample, you'd like to have the percent of deuterium very high. And we saw this a little bit in one of the problems, is that by changing the solvents, we can sometimes move the peaks around. And this is more or less just a trial and error to, if you have a sample that you're looking at and the peaks are always overlapping and it's hard to tell, you might just try a different solvent and maybe your peaks will be more dispersed. Okay? The other thing that we talked about is where, for example, the water peak will show up, right? Because if the water peak is just right on top of signals of interest, or if the solvent peak is right on the an area of interest, you might want to choose a different solvent to move those out of the way. So for example, here's the list of the residual protons in the solvent. So here's the 7.26 for chloroform. You know, there's the signal for acetone and DMSO and benzene, acetonitrile, methanol, and D2O. Right? So we can see where those signals show up.
And that's the expensive methanol, right? Because you can do CH3OH, D, right?
You
And
do
that's
G1
cheaper.
methanol.
Yeah.
Right, but D1 methanol isn't good as an NMR solvent. Right? It might be good if you just want to do a chemical exchange. Right? But if you're going to use it as an NMR solvent, you'd like that methyl group to be deuterated as well, or else it's going to give a huge methyl group in the proton spectrum. Likewise, you can have CD3OH, you know, but usually you want D4 methanol as an NMR solvent.
That's the expensive one in the ampules usually,
Right.
right? Okay.
Yeah, a lot of these you buy just kind of in single-use ampules, unless you really use it a lot. Because a lot of them, they will also kind of suck up moisture if they're, you know, open for very long.
Do you like using calcium hydride under vacuum for yours, or what did you use to keep them dry if you had to?
Well, I think usually with synthetic samples, when I was just using deuterium, it didn't matter that much. You know, I know some people that put molecular sieves in there as well. But, you know, you run the risk of contaminating your solvent that way as well.
Yeah, I'm okay with seeing a water bead.
Yeah, and you know, if you have reasonably strong synthetic samples, then I never had to do that.
Okay.
So then over here, the other interesting thing is the water. Oops. Right? So this tells us that in deuterated chloroform, the water peak is about 1.56. Right? But if you wanted to move that away, out of the way, and you wanted to have a solvent that another non-polar solvent, what we used to do is oftentimes go to benzene. The residual solvent peak is pretty close, 7.16, but notice that the water peak is moved all the way to 0.4 parts per million. So now the water is out of the way, and it's not going to overlap with hardly any other signals. Right? If you need a more polar solvent, though, to get it to dissolve, you know, then you can use, you know, methanol or DMSO. Dissolves almost everything, but it's kind of a pain. If you have to recover your sample, it's hard to, you know, pump it back off, too.
Say goodbye to that thing.
Or they don't even have it here. Is the deuterated pyridine is another NMR solvent that's reasonably common.
Isn't toluene?
Well, toluene's not so common, I don't think. I think it's really expensive because you got to deuterate both the benzene ring and the methyl group on there. And then in this table as well, going down this direction, it just shows some common contaminants. You know, for example, at the bottom, and this table in your book is bigger than this. I just chopped out part of it. You know, diethyl ether in chloroform, or diethyl ether in benzene, or diethyl ether in methanol. You know, it tells us what all these chemical shifts are in different NMR solvents. So it's a very practical table. Okay, so the last two experiments I wanted to talk here about on one-dimensional proton NMR. The first one is I'm calling selective spin decoupling. And so what this involves is using a second radio frequency that you selectively place on top of one of the signals in your spectrum. And what it essentially does is they kind of use the word, it kind of saturates that signal, or one of the definitions was that if you think about that proton is having two different energy levels, one aligned and one opposed with the external magnetic field, what happens when you apply that second radio frequency is it causes those spins to continually to switch back and forth very rapidly, and what it does is it removes the coupling to that proton. Okay? So we irradiate a second signal with a radio wave, and it removes any coupling that that signal has. So if we had two doublets, if we irradiate this doublet, this one over here will collapse to a singlet. It won't see that other proton anymore. Okay, so so far all we've been doing is trying to match up coupling constants, but this is our first direct experiment to show definitive coupling. Okay? So this is just a spectrum of a compound that we had isolated back when I was first a professor. And we just wanted to determine the different couplings, what couples to what in this spectrum. And because those signals are reasonably well dispersed, we can just put a cursor and put that second radio frequency on one of those peaks. So this is what it looks like with no decoupling. Okay, this is also with no decoupling down here. So this is our standard. And in this one, this peak right here has been squashed flat, right, with the decoupler. So then what we do is we compare all the other peaks and we look for what has changed. Okay, so what do you see that's changed? Yeah, this one right here, right? It was a doublet down here, and it's mostly a singlet up here. So that means that those protons that give rise to those two signals couple with each other. All right? And just to check it, what you'd usually do is then go and irradiate that one and make sure that it goes back the other way. So again, here we place our decoupler right here, and this one is definitely changed. Right? So one of the things that you can vary with this as well is the amount of power that you're applying on the decoupling. And if you increase the power, you'll get a more clean, this signal would go to a more clean singlet. So it looks like it's not being completely decoupled right now. However, when you do that, you usually hit a bigger window here. That peak will, the decoupling range will get bigger and bigger, which doesn't really matter in this case because there's no other signals nearby. But if you're trying to irradiate a signal and you have other protons close by, then it starts to become more sloppy, right? You start hitting more than you want. Okay, so this clearly shows again that those couple with each other. If we can go in and look at these next ones. So here's another one. It's decoupling here. And what has changed?
Something's changed between the two peaks there.
Down here, right?
Something's changed.
So that's changed. It's hard to see what it is. I think it has a methyl group and it has a water peak next to it. Alright, so let's just continue. Okay, this one has irradiated here. What's changed on that one? Probably the same one. Right? And so let's hit that one. Okay, this one got hit down here. And both of those collapsed. Right? So it looks like this is just a CH2, CH2, CH3. Right? And the CH2 in the middle is this one here. Okay, so these type of experiments are pretty quick and easy to run. So if you only need to know a couple of different couplings. You know, Stephen, this is something you could do on some of yours when you have those mixtures. If you know that one signal doesn't have overlap signals, if you could go in and decouple on there, you could clearly see what changes in, you know, some signals that are overlapping with each other. The other thing that it can help you do is if you have a multiplet that you can't really tell, if you irradiate one signal that couples into that multiplet, it will simplify the multiplet. And so you might be able to see what's left over, right? If it's a doublet of triplets of quartets or something, if you can remove the quartet component, then you only have a doublet of triplets, and you might be able to see that now and be able to measure the coupling constants, right? So it's a way you can also simplify the signals. All right, so the last thing that we're going to just kind of mention here is this thing called the nuclear Overhauser effect, or NOE. And what this involves is we irradiate a signal just like we did in the decoupling. Okay, so we irradiate it, but in this irradiate, and I didn't say it on the other one, when we're decoupling, we're actually irradiating during the acquisition. Okay, because we want to squash that thing while we're detecting the signal. In this one, we irradiate during the pre-acquisition. Acquisition. So that's that delay before the pulse. And then we usually turn off the decoupler during acquisition because we're not trying to actually decouple it. So what happens is we irradiate one signal, and then the T1 relaxation, which passes energy to other atoms in the molecule, cause protons that are in close proximity to be enhanced. So sometimes you hear it called NOE enhancement. So we irradiate one, some of the signals pass to a nearby proton, and so that proton gets bigger. Okay? This works in this way for small molecules. You know, maybe molecular weight lower than, I don't know, 600 or something like that. As we get big molecules, then these NOE, there's a range where the NOE goes through 0, and then it becomes negative. Okay, we'll talk about more about that when we talk about 2D NMR. Okay? So because these enhancements, they can be up to 20% enhancement, but oftentimes they're much smaller. And so we typically run these as difference spectra. So what we do is we record a reference spectrum which has that decoupler set somewhere off resonance. Right? It's not on a peak. And then we run one where it's on resonance, and then we subtract that resonance one, from the on resonance one. We subtract the reference from the on resonance spectrum. And so the reason we do the difference spectrum is because then we only see that the signals that have actually changed. Right? Because it's hard to do an integration and see, oh, this one's 5% bigger than it was before. It's hard to measure that difference, but if you do the difference spectrum, then everything else is gone, and only the one that changed 5% is showing up. Okay, it makes it easier to. Okay, so here's a few examples. So what happens is that the position that you irradiated. It gets squished, and then you subtract the reference spectrum from that, and so it ends up being negative. So we see that negative peak is the one that we irradiated.
Is this our homework problem?
Yeah, maybe. It's a different aspect of it. And so what we're seeing is that HA is close to these other three protons. Okay, but notice that only some of them are showing up, right? Some have been subtracted. Here, we're almost done. those. We irradiated another one here, and we see back to these. Right? And so this is a way to determine. Here's another example. When I was in grad school, I synthesized these compounds, and it made both the cis and the trans ring junctions. And so where I irradiated this one right here, okay, so I think this was H6, and this is H7 and H1. And in this case, when these were all on the same side, to do NOE, oh, I didn't really. So irradiated H6 is the one at the ring junction, and you can see small enhancement at H1. Oh, it's H7 is the one that's next to that isopropyl. So this confirmed that that was a cis ring junction, right? Because you can also see signal around cyclohexane rings. You can see, you know, NOEs between diaxial protons and things like that. Okay, but only up to about 4 angstroms or something. It's just a small distance through space, so it has nothing to do with coupling, right? So the NOE, they could be far apart in bonds, but if they're pushed close together in proximity, then we could get an NOE between them.
Does this work with the metal center?
Well, as long as it's not causing things to relax too fast and stuff like that. I don't know if it would work with paramagnetic.
It'd be cool to see how the ligands are interacting with each other through space.
Right, if they're close enough.
Yeah, to figure out, because we know the crystal structure, but that's in solid form. If
Uh-huh.
it's in an actual solvent,
Right.
to know